Starting from today, we start part B of Module 5, Quicksort. So this is a very important sorting algorithm. All right, part B.1, Introduction to Quicksort. All right, so first, let us look at why we need to develop a new sorting algorithm. The goal, the emphasis for this new sorting algorithm, we want to have a very good overall performance. Yeah. Here, when we talk about this overall performance, we want the best average case efficiency. Average case efficiency. All right. Yeah. So we work on our problem number 4, sort an array. Yeah. But here, I would like to do a small summary. Yeah. We have learned several sorting algorithms. Yeah. Here, I just want to mention 3 of them with different emphasis. Yeah. All right. Because when we look at the best case, worst case, average case, so you can see different sorting algorithms, they have different emphasis. All right. Yeah. So let me look at this. All right. Insertion sort. Let me use insertion sort. All right. Insertion sort, it has the most important property it has. It's best case. Best case is in big theta of n. That is the best among all the sorting algorithms. The best case. All right. Merge sort. Its worst case, big theta of n log n. That's the best among all the sorting algorithms. Now quicksort. All right. This time average case. Still big theta of n log n. We will see that later. Yeah. Still big theta of n log n. But if you do the real world application or experiments, you will see its average case is better than all other known sorting algorithms. Yeah. So that's another reason you can understand. So why we need to develop so many different sorting algorithms, because they have different properties. Yeah. All right, so let us look at the divide and conquer approach. How do we apply divide and conquer approach on this new sorting algorithm? Yeah. The goal, yeah, we already talked about that. Make the overall performance as fast as possible. Yeah. Number 2, in order to do that, we need to pay something, right? Yeah. Nothing is free. Yeah. In order to get this good property, so you have to pay somewhere else. Yeah. So number 2, that is what we are willing to pay. Tolerate poor worst case performance. Sometimes there is a bottleneck. The worst case performance for quicksort is pretty bad. So that's why we say tolerate. Yeah. Tolerate poor. Yeah. Pretty bad. Yeah. if you compare with the merge sort, it is really bad. Yeah. Later you will see that is the big theta of n squared. Worst case. Pretty bad. Yeah. But that's the cost we have to pay. Right? Yeah. But fortunately, number 3, the probability of the worst case is very low. It could happen, but the probability is extremely small. Yeah. So then when we look at the average, it won't be very bad, right? When we look at the average, it won't be very bad. Yeah, so that's, something we can take. Yeah. Next, let us work on the divide and conquer details. Change view on divide and conquer. Here, when I talk about change view, we compare it with the merge sort. In the merge sort, we take certain view, right? Divide and conquer, certain view. But here, we use a completely different view on divide and conquer. Yeah. So let us do comparison. All right, so here I do a chart. I list the key steps, compare merge sort and this new idea. Yeah. All right. First, you can see the divide step for the merge sort. The easiest. Yeah, split right in the middle. That's the easiest divide step. So big theta of 1. The efficiency. All right, yeah. Then conquer recursion. Yeah, so we, for the typical sorting algorithm, the conquer part, we use recursion. Now, pretty straightforward. Yeah. Then the combine step for the merge. Then we need to do a lot of comparisons. That's the main cost we need to pay this step, big theta of k. All right, yeah. But now the other possible view we can take, yeah. Conquer step, same recursion, we don't worry, but you can see we put our investment in different places, yeah, or just the opposite to the merge sort. Here, we want to make combine step as fast as possible. Yeah. Make the combine step as fast as possible. That's a totally different new idea, right? Yeah. But you have to pay somewhere else, right? If you save significantly in one place, you have to pay somewhere else. The divide step, we have to pay a lot. Big theta of k comparisons when we do the divide step. So from this chart, you can see these two views, divide and conquer views, completely different. Yeah. All right. So here, yeah, because here we use k, not n, so that means the data size of the current subarray, right? Subarray, yeah. All right, so then that is the new idea for this quicksort. Yeah, so next we just implement this new idea. All right, so let's look at the implementation part. Yeah. How to make the combine step easy. Yes, let's answer this question. Make the combine step as easy as possible. We need to do a lot of work. Okay? At the divide step, we need to really do some important work that we can enjoy easy combine of two subarrays, that property, right? Yeah. Okay. Our goal at the combined step, we want to do almost nothing in the combined step. So what do you mean almost nothing? So you can see after we do divide and conquer, we're almost there. We're almost there. Yeah. So let me explain using a diagram. Suppose we have two subarrays, A subarray and a B subarray. All right. After divide, we have these two subarrays. How to do the divide? That is our next question. Here, we cannot answer this question because that is a very complicated question. So we delay it. Here, we just assume after divide, we have these two subarrays. Before conquer, what do we have? Before conquer, what property do we have? Each subarray not sorted. Not sorted. That's the main property. Before conquer, but after conquer, each one is sorted, right? Each one is sorted after conquer. All right. Next, when we combine these two subarrays, we want to do almost nothing. That means you should not move elements here and there, right? If you move even one element, then you need to do something, right? Do quite something, right? Yeah. But we don't need. Yeah. The ideal situation we want to have when we combine them, we just put them together, we get the whole array sorted. That's what we want. The whole array is automatically sorted. We just put them together. Is that possible? Is that possible? Yep. It's possible. All right. So you can see at this step, there is no costly merge step. No costly merge step. See? Yeah. That's the important property we want to have. All right. Yes. So here, the goal after conquer, when combined, do nothing. Do nothing. All right. Yeah. Yeah. But how can that happen, right? It's nice. It looks really nice. But how can that happen? Here, let me describe the critical condition we need when we divide the data into two subarrays. What condition should we have? If you have that condition, then you can enjoy the property, do nothing at the combined step. Yeah. So what's that property? What condition do we need before conquer? Right? Yeah. We can make assumption. Yeah. If you are allowed to make some good assumption, can you find it? Right? Yeah. The condition is so simple. This condition. What's that? Yeah. Each value in the A subarray is less than or equal to any value, any element in the B subarray. Each element in A subarray is less than or equal to each element in the B subarray. How about that? Okay. Another way you can view is the maximum value in A subarray, A max, is less than or equal to the minimum value of B. How about that? Can you have that property? Can you imagine? Yeah, so let us just imagine that property. We can make assumption to have this property when we do the divide, right? Yeah. Yeah. So you can see if we have this property, then our combined step, do nothing, put there, you're done. Yeah. All right. So let us look at a little more for this important divide step. Yeah. Requirement. How to split here, the key step. You can see the key step, the divide step. How to split the array into two subarrays, A subarray and a B subarray, such that the key condition we want to have, A of I less than or equal to B of J. Yeah. We only need this condition. Yeah. But you should also notice we do not require A subarray, B subarray are sorted, because sorting these two subarrays, that's the job of the recursion, right? Yeah, when we call recursive function, we automatically, we get them sorted. We need to do a lot of work, but we take care of the sorting part, right? Yeah, conquer, we take care of the sorting part by recursion. But here we cannot assume A subarray. So the point here is, do not assume each subarray is sorted. Not necessary. Yeah. And this is the key inequality we need when we do the divide. How to do it? Next video, we will see the details. How to make this condition happen. Yeah. All right. Yeah. Let's finish.